Comes on everyone. So this is the last thing that we did. Where are the rest? Just wait for a minute. So hope everyone has just gone through this thing. So whenever you differentiate a vector, you get a dA by dt a cap and omega cross a bar. So this is what we proved last time. Now again, the derivation, what we are going to do now, frankly, the derivation is nearly not that important. The end result is kind of important. We will see some variations of it. All this is officially not there in the portion. So whenever they give you any question on this, they have to explain you and then they have to ask. And then they do that. So let's now when we got that equation there, if you actually write it down, you can think of like this. So if you take a vector r bar and if you differentiate that, so let me write like this. So if I say RAB, so this is a vector from B bar to AB bar vector. So the meaning of this is position of A with respect to B. So that is the meaning of this. So if a person B is looking at A, we'll call it RAB. AB is a subscript. Okay. Now, from the last thing that we derived, if I try to use that same formula here, you will see something here. So DRAB by dt, that would be DRAB by dt plus omega cross RAB. Now, what does this mean actually? So let's try to interpret it. Like I said, mathematically, we are really not that keen on what it means. Let me ask you a simple question. Like when we say V relative, the thing, what we did so far, when we say V relative, we always doing in translation. Let me show you like this. Let's say we have a person here, B here, and let's say there is a particle here, A. Now, till now, what we're doing, when we said relative velocity, we are writing simply VA minus VB, and we are done. Fair enough. But what happens is, till now, we have done all the problems in translation frame. Now, imagine a scenario where this person B is rotating his head with omega. Meaning, just think of like this. You're looking in front of your screen, right? Just look in front of you. You can see your screen or something. Now, if you rotate your head to the right side, relatively, you think the screen is going to the left, isn't it? Is that making sense? When you rotate your head to the right, you think the screen is going to the left. That means you can also get relative velocity, not only because you're moving, but also because you're rotating your head. So that means whenever you're rotating with omega, you will think A is going back with R omega. Is that making sense? So when B rotates the head by omega, B thinks A is going back with R omega. A is at rest. A is not going anywhere. B is at rest. He's simply rotating the head. A is also at rest. So no one is moving here. Everyone is at rest. But just because you're rotating your head, it gives you an illusion A is going back. So that means you can actually create relative motion by also rotating your head. B thinks A is going back by R omega. If you try to write this in the vector form, this is your R bar. Omega is out of the plane, so omega cross R. This would be omega minus of omega cross R. That is a vector form. So basically this omega cross r is the relative velocity because of rotation of the head. So this is how we can write everyone. When you say VAB, there are two components actually. VAB translation, this is what we have been doing so far, plus VAB rotation. So there are actually two components of relative velocity. We never cared about the observer rotating the head. We always thought observer is just going in a line. We never cared about rotating frames basically. Now, if you see that perspective, now you can clearly see this guy is looking like the translation component and this guy is the rotational component. Now, let me explain you more. Let me give you some examples, then we will do it in more better. Look at this example. Let's say we got a rod, which is hinged here. Let's say we have a point A here, and let's say we have a point B here. Let's say this distance is small r and this distance is capital L. Now, if I ask you this question, and let's say this whole setup is rotating with omega, what is the relative velocity between A and B? If I ask you this question directly, what is the relative velocity between A and B? What is the answer? Think about it. If you are B, if you're standing here, and if you're looking at A, no matter how much it rotates, do you think, is the distance between A and B changing? Don't you think A is always in front of you? If you're just looking there, sitting here and looking at A, don't you think A is always in front of you? So technically, B thinks A is at rest. That means velocity of A with respect to B is always zero. There is no relative velocity between them. But let's try to solve the way which we know. You will see the problem there. What is B ka velocity? From circular motion, so this speed will be r omega. What is A ka speed? VA will be L omega. So if I use kinematics, relative velocity, velocity of A with respect to B, what we used to write? We used to write VA minus VB. So that will be L omega minus R omega, J cap. This is not zero, did you see? Isn't that how you find relative velocity? But the catch is, this is a translatory frame. We never cared about B rotating the head. The person B who's standing here, his head is also rotating. You're spinning. So we have to take the second part. Now look at this thing. Now when you ask B, what is A doing? B will say, I'm rotating my head with omega and the distance between us is L minus R. So because of this, I think A is going backward with L minus R omega minus J cap. So velocity of A with respect to B because of rotation of the head is minus L omega minus R omega J cap. So there are two relative velocities. One is coming because you both are traveling, translatory. Second thing is coming because the observer B ka head itself is rotating. When you're sitting there on that rod and you're rotating, your head is also rotating. Now, when you take the relative velocity A with respect to B, I need to add both the translatory relative velocity and rotatory relative velocity. So that will be, I'll just write VAB translation plus VAB rotation. Now, when you add, then you'll get a zero. Is this logic making sense, everyone? Because when you're standing at B and looking at A is never moving. A is always in front of you, right? B should be moving with minus J cap, right? As A is rotating. What are you asking, Ahana? You're standing at B and looking at A, right? B will think what? I'm at rest, my head is rotating. The last case, it's L minus R, right? See, I don't care about A. If you rotate your head omega clockwise, you think everyone is going anti-clockwise, isn't it? So here B is there. See, B ka eyes are this. Now, when the rod is rotating, see what happens. When the rod has come here, B ka eyes are here. So B will think my head is rotating with omega, isn't it? So he will think A has gone back. Clear, Arnav? So you're looking at the this omega is the observer ka omega. It is not the point A ka. Is this making sense, everyone? So this is what I was writing here. So when you rotate your head, even then you get a relative velocity. So there are two things here. So that means when you write that formula, this is how you can write it. So velocity of A, B, let me write this in a rotating frame will be velocity of AB in the translatory frame. This is what we used to do in kinematics, VA minus VB minus omega cross R cap. So this extra thing is coming. So this is the velocity of A as seen by the rotating frame. So when this is the case when B is rotating the head. So this is how you read this. Velocity of A as seen by B. So here what we are doing here, B is moving, B is translating and also rotating his head. So think of like this, you're walking straight and then you're also rotating your head and looking at something. So that is the reason you get two components. This is coming because of translation. And this is coming because of rotation. So this is the relative velocity due to rotation of head. That's it. So that much you just understand what is happening. So when you rotate your head, you get a relative velocity. Yeah, so it is basically the same thing here. So if I shift it this side, this will become the rotating frame and this will become the relative velocity in the translatory frame. But I think this is more intuitive. Is this making sense? Suppose if the person ka head is not rotating, then what will happen? Omega will become 0. Then velocity of AB in the AB frame is translatory frame only. Any doubts on this? Everyone clear with this story here? Then we will do a little derivation there again. Don't worry too much about the derivation. The end result is more important. So when we write this formula here, so VAB, I will just start writing like this. I'll put ROT, meaning rotating frame. That is the meaning of it. VAB, I'll put capital T for translatory frame is minus omega cross R. So this can be written as d by dt RAB. I can shift it this side. I'll get VAB. Translatory frame is VAB, rotatory frame, plus omega cross R. This is nothing but d by dt of RAB. So what was this velocity? This is the velocity of B of A when your head is rotating. It's that component. Now, if you differentiate both sides with time, the left-hand side will become d square by dt square RAB and this guy. And remember, just how I taught you in the last thing. Anytime you differentiate a rotating vector, you get actually two components. So here, every vector is rotating here. But I'll just write it down again here. So dVAB by dt, when you do this, you end up with dVAB by dt, the magnitude, plus omega cross VAB bar. So this is nothing but acceleration of AB plus omega cross VAB. So this guy will become acceleration AB plus omega cross VAB. Plus when you differentiate this, we will get d omega by dt. This is again RAB plus omega cross drAB by dt. But drAB dt is nothing but this guy again. Yeah, it becomes a big mess actually. You got a big thing. This is the acceleration in the rotating frame. So omega cross VAB, d omega by dt becomes alpha. And this guy will be omega cross. We have to multiply this whole term again. We get omega cross VAB plus omega cross RAB. That's a big one. Again, like I said, don't really too much worry about the derivation. I wanted to show you what you get in the final terms there. So now if you just simplify this, so if you see this thing here, this is the acceleration of AB in the translatory frame. I'll just leave it as d square by dt square RAB. So now if you bring this thing here, acceleration, this is the acceleration in the inertial frame. I can just shift it this side, bring it this thing here, acceleration of AB in the rotating frame will be d square RAB by dt square. Shift everything that side, you'll get minus omega cross r cap minus alpha cross RAB minus 2 times omega cross VAB. Multiply mass on both the sides. So mass into acceleration of AB in the rotating frame. So that will become force in the rotating frame. This will become m into d square RAB dt square. Remember here, omega and alpha are the angular velocity and angular acceleration of the observer ka head. It is not the object which you are watching. This would be alpha cross RAB and minus 2 omega so this would be the force in the rotating frame, because mass into acceleration in the rotating frame will give you force in the rotating frame. So when you go and stand on a body which is rotating, you think this is the acceleration in the ground frame, this is the force in the inertial frame, or the real forces. This would be your centrifugal force. If you look at that, it looks like m omega square r. Yeah, that's the vector form. This is your, if you see alpha b, that is your tangential force. This is called Coriolis force. Just have a look at the steps. You can see what I did. We started the whole story with this. We said whenever you want relative velocity, there are two things happening. One is your regular relative velocity. Second thing, because you're rotating your head, the velocity will be omega r backward. When I differentiate this, I got multiple terms actually. So whenever I differentiate a vector, you have to you'll get something like this plus an omega cross. This we proved in the last time. So when you differentiate this, so I got two terms here, and for this I got two terms here. And RAB is again this full thing. When I substitute here, it expanded. I got a pretty big stuff. Yeah, luckily you don't need this derivation. But let me show you finally what we got. This is your centrifugal force. This is your, it's called Euler's force. This is called Coriolis force. So that means whenever you actually go and stand in a rotating frame, you will see multiple sort of forces. It's not a single thing. Just have a look at the steps. I know it's pretty big, but just try to understand once. Start from here. Have a look at this once. And this thing, right? Wait, I forgot to expand one more thing here. So this would be m into acceleration of A with respect to P. If I expand this, actually, I get one more force here. You'll get m into acceleration of A minus m into acceleration of AB. This will be your linear pseudo force. This is four pseudo forces. And this MA will be the real forces. Those are the real forces acting on A. So force, you can see like this thing. Let me write it like this. This is the forces on A as seen by B. This is forces on object A as seen by a rotating observer B. That is the full form of the left-hand side. So because the observer is rotating, all the forces you will see M into A is all the real forces. These are the actual forces acting on A. This MAB will be your mass of B into acceleration of B. That's your linear pseudo force. So this is MB into omega cross RAB. This is your centrifugal force. M into, again, that is also B only, M into alpha RAB. Yeah, there's a lot of terms there. Let me show you how to use this though. That's more important. And minus 2m omega. So this is your pseudo force due to this. So when you take all these four terms together, this is called pseudo force. So when an observer is rotating, you don't get one pseudo force, you get actually four pseudo forces. What you have done in NLM was only this one pseudo force, M into AB. But when you rotate your head, you get this many pseudo forces. Centrifugal force there's also something called Euler's force, and there's also something called a Coriolis force. To put it in a more simpler terms, I can write like this. F rotating will be F real minus, this is nothing but your centrifugal force. I'll put it in another way. But there, that's the whole meaning of it. Just have a look at the equations again. I'll explain you. Listen, we'll start with this. First thing, whenever let's say if A and B both are moving, then the relative velocity is VA minus VB. So this guy is VA minus VB. But this is only due to translation. One. Second thing, now your observer B is not also moving, but he's also rotating his head. Now, because you're rotating the head, you get a relative velocity due to rotation. This is omega cross R. We always used to ignore this because we have always taken our observer to be a translatory frame. We never cared about his own rotation. But now it will matter. If you're taking an observer who is rotating his head, it's going to affect a lot of things. Is that part clear? Now, for that, the best example is this problem. If you look at this problem, if you ask B, what is A ka velocity? If you just use translation, then the relative velocity is L omega minus R omega. But if you're standing at B and looking at A, you will think A was never moving. So how do you explain that? Your translatory relative velocity cannot explain this. That is because your B, when he's looking this way, when the rod rotates, even B ka head is rotating. Did you see B ka head rotated? This gives you an illusion A has rotated backward. So the translatory relative velocity and the rotating relative velocity got cancelled. And that's why B will think A is not moving. I hope this was an explanation was clear. This is a good example to explain that relative velocity of translation and rotation. And then we did differentiation. Yeah, this is little work there. So when you differentiated the quantity, I shifted the translatory there, rotating there. I differentiated. So and this was another big headache actually. That's why this is not there in the portion. So for your understanding. And then we get all these things, then we get all these terms. So if I have to just put it in a normal way, this is how it will look. So pseudo force is not one single thing. There are multiple forces on this. So centrifugal force is different. This is different. So yeah, I'll just remove all that cross products and everything. So F rotating will be F real plus M into A B. This is your linear pseudo force. Minus M omega square R. This is R cap. Plus M omega square R cap. This is centrifugal force away from center. This would be R alpha plus 2V omega minus theta cap. Don't get confused using all this terms. You don't need all this. Let me explain you. This is a centrifugal force. And there is a mass also here. This is your Euler's force. This is the tangential acceleration, and this guy would be your Coriolis force. So we are mostly interested in the Coriolis force and the centrifugal force. Now listen to the cases. So VR is the radial velocity. Omega cross R, it comes from here. See. When you're standing here, this is your R bar. And when your head is rotating this way, this is your velocity. this will be omega bar, isn't it? Right, Karthik? So omega cross r bar will give you this direction. So this will be the direction of omega cross r bar. Cross product. Clear? Omega is out of the plane, r bar is radial. So if you do omega cross r, it will come tangential. So that is how you get that there. Okay. Now listen to the examples. Like this will make things more clear. So the only thing I want you to know from for now is this: pseudo force is different, centrifugal force is different. So don't mix it up. Now when you take uniform circular motion, right? Alpha is 0, right? R is constant. So this V radial is nothing but dr by dt. So V radial is 0. So literally everything goes off. So the only thing that is left is pseudo force. M omega square r. R cap. This is nothing but the centrifugal force. Away from observer. Now, listen to the examples. You'll get things cleared. I'll show you how to use all those things one after another. So centrifugal force is what? M omega square r cap. What is r bar? Be careful. R bar is a vector from the observer to the object. This is not the position vector. Vector from observer to object. Now let's do a question like this. You will see how to handle this. Let's say we got a disk. The disk is rotating with omega. We have a coin here of mass m. And let's say the disk is rough mu. The question is simple. And let's say this distance is small r and this distance is capital R. So the question is find max omega. Means if you rotate the disk very fast, the coin will slip. Find max omega so that the coin does not slip. Now let's ask 3 people to solve the problem. Let's ask the person A on the ground. A is on the ground, he is at rest. We will ask him to solve the problem. Then we will keep one observer at the center, B, and we'll ask him to solve the problem. We'll keep one guy, C, on the circumference, standing on the circumference. We'll ask him to solve the problem. We'll ask one guy here who is on this part and ask him to solve the problem. So we'll ask these 4 people to solve the problem. So officially we should get the same answer, but let's see what they will draw. Is the question clear? The coin is on a disk at a distance of small r and this thing is rotating. And we are asking all 4 of these people to solve the problem, find max omega so that it doesn't slip. So first let's ask A to solve the problem. So this is the coin. It's going in a circle of radius r. Now, if you ask A what you're doing, he will say, I'm in inertial frame. No one is moving. The observer is not moving, is not rotating his head, is doing nothing. So there will be no pseudo forces or anything. So in his frame, pseudo forces 0. Now, if you ask him to solve, he will say, okay, the forces are normal reaction, mg, and friction. That's it. These are the 3 forces. And he will say, since you are going in a circle, there will be a centripetal acceleration. This is what we did last time, which is omega square r. Perfect. And then he will write the equations. N is equal to mg. friction must be balancing the centripetal acceleration, which must be less than or equal to mu into n. So he will say m omega square r is less than mu mg. And he will get omega is less than or equal to mu g by r. This was easy. This was straightforward. This is what we have done last time also. The coin does not slip. This is what the guy on the ground will say. Perfect. Now let's ask B to solve the problem. B is standing at the center. So technically is not moving. There is no translation motion, but B ka head is rotating. Right? If you look at B, right, B is also rotating with the disk. So B is rotating here. So if you ask him to draw the forces, so that's the problem here. Whenever the observer starts rotating, you start getting all pseudo forces. B is rotating his head. Basically, you're just standing there, and I can say head of B is rotating. Even though he's not moving. Great. Now, if you ask him to draw the forces, he will say, okay, there is a normal reaction. There is an mg. There is a friction. And then he will say, there is a pseudo force. Now, which pseudo force? Listen to this thing. There are 4 pseudo forces we have to use officially. The first one is 0. Why? B is not accelerating. There's no translatory motion for B. So this guy is 0. There's a centrifugal force? Yes. Is there an acceleration? No. So this guy is 0. Is there any velocity between them? No. This guy is 0. So out of the 4 pseudo forces, we will just use this one guy. So he will say there is a centrifugal force, which is m omega square r. And this is also the pseudo force. So in this case, pseudo force is the centrifugal force. And when you ask him to solve the problem, he will say acceleration is 0. He will say coin is never moving. So B thinks coin is at rest. It is always in front of me. Then we will write the same story. We'll write n is equal to mg. Then we'll write f minus mg is equal to 0. Then f is equal to m omega square r is 0. F is m omega square r is mu mg. And yeah, same story. We'll get the same answer. Perfect. To apply linear pseudo force, B should be accelerating, right? What is the acceleration of B translatory? Is B going anywhere? He's just standing at the center, right? You're just standing at the center. Your head is only rotating. So is there any translatory motion for B? No, right? Now let's ask C to solve the problem. Yeah, this understanding is important because in terms of solving, we will always solve in Bika frame, but they can ask theoretical questions and then you'll get stuck. So at a mains level, you really don't care about all this stuff, but advanced we never know. Now we are asking person C to solve. Now C is also accelerating. C himself is going with an acceleration omega square capital R. This is the acceleration of C. Matlab C is having an acceleration now. And now if you ask C to solve the problem, he will say, okay, there is a normal reaction. There is an mg. There is a friction. Perfect. He will say till here. And he will say the distance between me and the coin is now r plus small r. So the centrifugal force is m omega square r plus small r. Remember that small r is the distance between the coin and the observer. This is your centrifugal force. So this is the mistake people do. Ask them what is centrifugal force, they'll say m omega square r. The question is, who is the observer? This is one centrifugal force. Second thing, because A himself is accelerating, there will be one more acceleration, m into acceleration of C, which is m omega square capital R. This is your linear pseudo force. So this pseudo force is coming because C himself is accelerating. And if you ask C, boss, what is the coin doing? He will say, coin is at rest. Coin is always in front of me. Now, if you ask him to write the forces, he will say friction plus the linear pseudo force m omega square r must be balancing m omega square r plus r. He will again get F is equal to m omega square r and then the standard story mu mg. And then you get omega is less than equal to root mu g by r. Now here, if someone asks you, what is the pseudo force? The pseudo force is the combination of all these forces, which is m omega square r plus r minus m omega square r. So the pseudo force is m omega square small r. What is the centrifugal force? The centrifugal force is m omega square r plus r. Both are not same. Are you getting the difference here? Now, again, if you go back to this equation, now the observer is accelerating. So linear pseudo force aayega, centrifugal force aayega. There is no tangential acceleration, there is no radial motion. So these two will be zero. You getting how to add things? So if someone asks you what is centrifugal force, your first question should be, boss, who is looking at the problem? Let's ask D to solve the problem. Actually, now you can take any random point, but let's see. I'll show the top view. The coin is here. This is the center and the D is standing here. So acceleration of D will be omega square r this way. Now, when you ask him to draw the forces, he will say, okay, there is a friction. There is a centrifugal force. What is the centrifugal force? Away from the observer. So this is the centrifugal force. M omega square. Let this distance be some x. M omega square x. This is the centrifugal force. It is always mass of the body, omega square, and distance between the observer and the coin. And if you'll also say, since I'm accelerating, there is one more pseudo force, which is mass into acceleration of d. This is m omega square capital R. This is your linear pseudo force. I hope this is making sense what is happening. There are two different pseudo forces. Now, when you draw the FBD, you can take this angle to be some theta. This is R and this is small r. So we have force is friction. We have m into omega square r. This is m omega square x. So if you resolve this into components, this will be m omega square x cos theta. But x cos theta is nothing but m omega square r. So that will cancel out. This will be m omega square x sine theta, but x sine theta is m omega square small r. Again, he will write the same thing. He will say f is equal to m omega square r, which should be less than equal to mu mg. And we get omega is less than equal to root mu g by r. So it doesn't matter where you stand. So if someone asks you again, what is the pseudo force? The pseudo force is sum of all these forces. The pseudo force is m omega square small r. It's always the answer. What is the centrifugal force? Now it will change. M omega square x. Are you guys getting what we did? So that's for your understanding. Okay? Now, if this is getting overwhelming, let's keep it simple. Whenever you're solving problems, remember, we will always keep the observer at the center of the disk. Okay? Let's keep it very simple. When you're solving problems, don't think so much. Keep the observer at the center of the disk. When you keep him at the center of the disk, linear pseudo force will become zero. There's only one pseudo force, centrifugal force. So till now, whatever you learned in school, right? The centrifugal force is m omega square r. The observer is always at the center of the disk. But if you keep the observer at different places, centrifugal force m omega square small r nahi hoga. It will change. Is that point clear, everyone? So we will never solve problems like C and D. Those are just for theoretical understanding. Whenever we solve, we'll keep our observer always at the center. So you are getting the centrifugal forces because the observer ka head is rotating. What about the remaining two terms? We will see them in the end. So let's not put everything together and confuse you, but I had to teach you this. Because if I just teach you centrifugal force, there are two more pseudo forces. You will never realize what are these. So yeah, in the last half an hour, whatever I taught you, if it went over the head, I want you to remember these two to three things. The first one is this guy. Whenever you're rotating your head, you will go backward by r omega. And this example, that's the first thing you should remember. Second thing, forget about all these things. Second thing, remember there are actually four pseudo forces. It's not a single pseudo force. The first pseudo force is coming because the observer himself is accelerating. Second pseudo force is coming centrifugal force. Third is coming because of tangential acceleration. The fourth is coming because the object is moving. We will talk about that last one later on, Coriolis force. That's the second thing. Third thing, when you solve problems, either you solve the problems in A ka frame or B ka frame. Never do it in C ka D. Don't confuse yourself. When you're standing at A, everything is at rest. Observer is not rotating, observer is not moving. So there are no pseudo forces. There's only centripetal acceleration. If you stand at the center B, B is not accelerating, but B ka head is rotating. Because of that, you got a centrifugal force. So whenever you write m omega square r, you're always taking about an observer who is at the center. Is that clear? That's it. These are the 3 points. Keep them in mind. That's the main important crux. Remaining things, they will fall in place slowly. We'll be doing it again during the revision also. That's the idea there. Because whatever, all that other pseudo forces are not in the portion. But I'll teach you at the end of the chapter a bit, 1 or 2 questions on that. And advancement, when they ask questions, they actually ask much easier. They won't do all these derivations. They'll give you the formula directly. Any doubt so far on this? This is where I'm more interested on. What is pseudo force and what is centrifugal force? People think both are same. They're not. Centrifugal force is one of component of a pseudo force. All clear with this? So I'll just put a note here. So when we solve problems, if observer is in the ground frame, then just use centripetal acceleration. Don't talk about centrifugal force. It doesn't exist. Definitely spend some time today or tomorrow, just 10 minutes, just go through that stuff. Try to understand the main points. If observer is in a rotating frame, when I say rotating frame, think of like this. Observer ka head is rotating. That is the meaning of rotating frame. When you stand at the center of the desk, you're not moving, but your head is rotating. If observer is in a rotating frame, here I'll mention something. Preferably, always choose the observer at the center of the rotation. That will make your life easy. You'll not get all that weird pseudo forces. Preferably choose observer at axis of rotation. Then you can get m omega square r directly. Now, don't mention, then use centrifugal force. Don't talk about centripetal acceleration. So if you use centrifugal force, don't talk about centripetal. If you use centripetal, don't talk about centrifugal. Clear with this? Let's see some questions on this. So all these problems I did before, you can do with centrifugal force now. Let's say we got a disk, top view, rotating with omega. We have a rod here. So the center is x is equal to 0. This is x is equal to r by 2, and this is x is equal to r. This is a rod of mass m and length r by 2. And this entire disk is rough. So when the disk is rotating, right? So the side view will look like this. Clear? So a rod of mass m is placed radially on the disk. On a rough rotating disk. Find omega so that the rod does not slip. Find the maximum omega. So if you rotate the disk very fast, the rod will slip. So what is the maximum omega? The side view will look something like this. Again, for simplicity, what you do, put the observer at the center of the disk and solve the problem. That makes your life easy. So this is r by 2 and this is r and this is mu. There, give it a try. How do we do this? So if you see at every point on the rod, the centrifugal force will be different. This is where centrifugal becomes really, nice. Like it gives you the feeling of a force. It's more easy to visualize. Let's see. Now you can do this in the ground frame also, but like I said, the observer, right? Let him keep at the center. Now, if you ask him to solve the problem, this is what he will say. At a distance x from here, take a small piece dx. Let's try to draw the free body diagram for this small piece. If you look at the forces here, there is actually a tension T. There is a tension T plus dt. I can even find the tension in the rod. That would be another good question. Find the tension in the rod. And there is also a friction df. Small friction will be this side. There will be a small normal reaction dn, and there is a small weight dmg. And there's also centrifugal force dm omega square. Check total 1, 2, 3, 4, 6 forces. And this will be df max. So this is the force on this one thing. Now what we can do, and what is dm? Dm will be total mass by length into dx. Length is r by 2. We get 2m by r into dx. So there is no need to find the tension. You can find it, but we can write like this. All the centrifugal forces are pulling the rod away from the center. The total centrifugal force must be equal to total frictional force. So all the frictional forces on the rod are balancing all the centrifugal forces. So that will be integral dm omega square x must be equal to integral df max. This would be 2m by r omega square x dx. This will be integral mu dmg. Dm is nothing but m by l, m by 2m by r dx into g. Limits will go from r by 2 to r and r by 2 to r. Integrate this thing. 2m by r will cancel on both the sides. This will become omega square x square by 2. Limits will go from r to r by 2. This will be mu g. This will be x. Limits will go from r to r by 2. Yeah, simplify this, and then you end up with omega square by 2. This will be r square minus r square by 4. This will be mu g r minus r by 2. Omega square by 2, 3r square by 4. This is mu g r by 2. 2 will cancel. We get omega is equal to 4 mu g by 3 r car root. This is your maximum omega. If you rotate anything faster than this, the rod will slip. So omega less than equal to root over 4 mu g by 3r is no slipping. So the point is this: every point on the rod is a different distance. So they have different centrifugal forces. So all the centrifugal forces must balance all the. dt becomes an internal force, right? If you take all the rods, what is tension inside? Internal. So they all cancel out. So we can write a note there. Sum of all tensions will be 0 if you take the whole rod. Yeah, but that is another good question. Find the tension in the rod. That, if you want, I can write the equation. You'll get dt plus dm omega square x is equal to df max. Now, if you integrate this, you'll get tension as function of x. That's another good question. They can ask you find the point with the maximum tension and so on. All clear with this? There, this is how we use centrifugal force. If you see whatever I taught you, right, you really don't need to know so much to do this problem. You just need to know there's a centrifugal force m omega square r. And the important thing, to use m omega square r, the observer must be at the center. But just keep that much in mind, you'll be able to handle most of the problems. When those weird things comes, I'll show you. Clear? Take a break. Come back by 9:40. We'll continue from here. Comes on everyone. Let's start off. Let's see one more. Let's say I have a big disk here. So we have a pulley here, we have a block here, mass m. We have another block here, mass 2m, and it is connected like this. And this whole setup is rotating with omega. Meaning if I just draw this side view, it will look like this. This is m. This is 2m. So this whole setup is rotating with omega. All surfaces are rough. So here the friction is mu, here the friction is mu. Find omega when the blocks are about to slip. And this distance is r. You can treat the blocks as point objects. So again, all our problems, we will always keep the observer at the center. Our observer is always standing at the center and looking at the blocks. So keep it simple. The centrifugal forces are pulling the blocks out. Give it a try. So they're placed on a disk and the whole disk is rotating. So the centrifugal forces are trying to pull them out. But they're also connected by a string. Hope the question was clear. Try. I'll give you a minute or two. Step 1, draw your free body diagram. Story is still the same. The only thing you learn in this chapter is the observer is at the center and there's a centrifugal force. Then step 1, free body diagram, equation, constraints, whatever. Let's see. So if you draw the free body diagram, so the thing is you need to be careful with the direction of frictions. Imagine there is no friction anywhere. What would have happened? If there's no friction anywhere, the lower block will have centrifugal force 2m omega square r. So that means the 2m block has a tendency to go out. So this is how the force will be, everyone. 2m omega square r. This will be tension. This will be tension and this will be m omega square r. You can clearly see if there is no friction, 2m has a tendency to go right side. That means this friction will be backward. This friction also will be backward. and this section will be F2. So the directions are important. That is how the frictions will be. Yeah, and then you're done basically. So tension will be m omega square r F2 max because you're about to slip. Tension plus F1 max plus F2 max is 2m omega square r. So this will be m omega square r and F2 max will be mu mg. Take this and substitute here. This is m omega square r plus mu mg. F1 will be 3 mu mg plus mu mg is 2m omega square r. We get m omega square r is equal to 5 mu mg. Goes off. We get omega will be root over 5 mu g by r. This is your maximum. You go anything more than this, the blocks will slip. Please check your forces, everyone. The centrifugal forces away from the center. The frictions will look like this because the 2m is trying to go to the right side. There is a friction on the floor and there's a friction between them. Any doubts on this? Clear, na? Ananya? Manav? Clear? Sumana? Shlok? Clear? Shlok? Tanmay? Soumya? Next one. Going ahead, any doubts, please ask me. The main thing is a free body diagram. If you got that, then it is done. Next one. This is another good question. We got a rod here. So you are catching one end of a rod and rotating with omega. This is x is equal to 0 and this is x is equal to L. And this rod is going in a circle. Neglect gravity. So if you're rotating this rod, the rod will have some tension. Find the tension in the rod as function of x. Rod of mass m length L rotates about its end. Find tension in the rod as function of x. At a distance x from axis. How did I get the friction? How do we get the direction of friction? Look at this. The 2m is trying to go this way. M is trying to go this way. Now you tell me what will be the direction of friction. Nah? Then you will get it. Because of that string, so that is a tendency to move. Get this, everyone. This is a pretty good one. Uh, this will be the basis for a lot of problems going ahead for other chapters. How do you find tension in the middle of a rod or something? So here, as you go away from the center, centrifugal force is increasing. Try. Take 2 minutes, 2, 3 minutes. Think about it. It's a good one. It's okay if you don't get it, but figure out the steps, 1 or 2. And remember the process. Next time when you see this, you'll be able to handle it. Right, Ahna. We have an answer. Another 1 minute, then I'll show you. Everyone should try. It's fine not to get it, but figure out few steps. Let's see. Right, Karthik. Now, before going ahead, few things here. This we wrote this statement even before also in NLM. I remember writing somewhere here. Yes. Free ends have zero tension. If you remember, there was a statement like that. So if you look at here, this is a free end. There is nothing connecting to x is equal to L. So that's an important thing. Free ends will have zero tension. So if you take a rod and you start rotating, the one which is not connected will have no tension because there's nothing to pull there. So here at x is equal to L, the tension is zero. So be careful with the limits there. Perfect. So take a rod. Now in the previous question, remember I ignored that dt. Now I will not ignore it. So I'll take an x. I'll take a small slice dx. So if you try to draw the free body diagram of the small dx, the forces will be, so few things here. We always assume tension is increasing with x. That is how we treat it mathematically. So this is something you need to know. Even though I know tension is decreasing as you go out, mathematically, right, we assume the functions are always increasing. Let the science take care of it. Let the angles be always acute. Let the tensions be always increasing. Anything, we always assume functions are increasing. The science will take care of it. We assume the functions are increasing. So that is the reason I'm writing t plus dt, even though I know it will be negative. The science will take care, you will see. That is t increases with x. That's a convention we follow. Makes your life easy, just keeps it simple every time, no need to think two times. The centrifugal force is dm omega square x. That's it, there is no other force. You can clearly see here t plus dt plus dm omega square x is equal to t. There I got dt negative. I thought it was positive, it will increase, but actually it comes out to be negative. The science took care of itself. And then what is dm? Total mass by total length into omega square dx. This is where you have to be careful, the limits. When x is equal to 0, tension I don't know. When x is equal to L, the tension is 0. This is a mistake people do. They put 0 to x and 0 to L and it goes for a toss. So be careful with that. So that will be tension minus m omega square by L. There is one more x here. X square by 2. Limits will go from x to L. M omega square L square minus x square by 2L. Check. That's your answer for tension. So be careful with the limits. So few things. First thing, free end have zero tension. Second thing, we always assume functions are increasing. And the third thing is the limits. So be careful with that. It's a good question. Not tough, but it's a process. Now we have seen this, and later on we will use this for pressure and lot of things. But the idea is the same. All clear with this. The next one, it's a very important question. It will come in 6 different chapters. Standard model. So you should definitely remember this. How to do this more than the result. I really wanted to know the process. We have a ring rotating with omega, mass m and radius r. Now, if you look at this top view, the every segment of the ring has a centrifugal force, dm omega square r. It is pulling away from the center. So the centrifugal forces are trying to stretch the ring. So that means this will result in tension in the ring. The ring will be under tension. If you can actually rotate fast enough, ring will get shattered. This is one of the problem you will face in in racing cars. You can't use your regular metals to create the discs and everything. These things have omega so high, the centrifugal force will crack the discs. So you have to use special alloys, high strength materials when you're building, race cars or something. Ever seen this in your car, right? Beside the speedometer, there is one more number, RPM karke. Observe, yeah, there'll be two things. One is an RPM thing, and one was the speed ka thing. That RPM is actually telling you how many revolutions you're doing. So that happens. You're going too fast, and the disc is rotating so fast. The inside the axle ka disc will get shattered. So find tension in the ring. More than the result, the process is important. Take a minute, think about it, then I'll show you. And this process, what I'm going to teach you now, will come in 6 chapters at least. So you should definitely know this. And a standard question in mains and CET comes directly, should just mark the answer and go ahead. Try, think, take a minute. Let's see how you approach this. So how do we do this? Listen to this. Yeah, it looks a little different than what you have done so far. So you should know the process. Matlab, I'm asking you to remember this. Ratta marlo. That is the thing. So you see this question and you should know this is how I should approach. There are a few things like that. So we will take a very small piece, d theta. So we will choose a very small piece. So this length will be r d theta. So there'll be two tensions. So one tension is pulling this way and one tension is pulling this way. So let me exaggerate this. So this is d theta. This is your tension. This is 90 degrees, and this is your tension. This was a 90 degrees. If you drop a bisector, this angle will be d theta by 2. This angle will be d theta by 2. And this angle will be, if that is 90 here, d theta by 2, this angle also will be d theta by 2. You can check out that from geometry. So if you take a vertical line, this will be d theta by 2, 91 is d theta by 2, d theta by 2. Perfect. So if you resolve these forces, this will be t cos d theta by 2. The vertical component will be t sine d theta by 2. T sine d theta by 2. The centrifugal force will be away from the center, d omega square r. Please have a look at this free body diagram. These are all the forces. You can clearly see cos components will cancel out. The two sine components of the tension are balancing the dm omega square r. Now, there's a small approximation for small angles. For small theta, sine theta is approximately theta. Be careful, this should be in radians. So example, if I say sine 3 degrees, don't say sine 3 degrees is 3. Sine 3 degrees, first I should write in radians. Sine 3 pi by 180 is approximately equal to pi by 60. That is the meaning of it. So for small angles, I can write sine theta as theta. So this guy will become 2t. D theta is so small, I can write sine d theta by 2 is approximately d theta by 2. That is the point of taking a very small slice. This will be 2t d theta by 2. dm will be total mass by total length. 2 pi r into length r d theta. That is the dm. Because for 2 pi r, if the mass is capital M, for r d theta, mass is dm. 2 will cancel, d theta will cancel. We get tension M is equal to m omega square r by 2 pi. This is the tension in the ring. You can clearly see there, if you make the omega double, the tension becomes 4 times. If omega becomes 3 times, tension becomes 9 times. So it's increasing as a square function. Please have a look at the process. So this is how you handle this kind of a problem. Take a small piece, draw the FBD, components, and yeah, check out the steps. Any doubts on the free body diagram? How did I write the equation? Anything you're not clear, please ask me. So how does this look like? Look at this. You
Hello, I'm Dan. And this is the slowest
You guys are able to hear the audio, right? Okay.
splenoidized video we've ever done. Pretty interesting. We're going to spin.
So what these people are going to do, you can see there is a CD there, and they're putting it on a spinner, and they're going to rotate it pretty fast. So you guys must not be, must have used a CD or DVD, but when we are in IIT, right, we never had this hard disk and all. Memory was costly, so we used to use a lot of DVDs and CDs. So one day I brought a DVD, and there is something called burning the DVD. Means you put data on the DVD. So I kept the DVD there, and I kept it at maximum speed so that it can done faster. And then I heard a big sound. So I stopped the PC, I opened it. Inside, the whole disk was shattered into pieces. I got the DVD for 50% discount. So I was happy, and I brought the disc, and it was so such cheap quality. The whole thing broke down. So something like that. So if you see here, they're going to keep a disc here and they're going to rotate it, and we will see in slow motion what happens to the disc.
CD, literally at warp speed, so it's going to go. We'll be able to
So
find pieces of
we'll
dust.
just skip it forward.
I'm scared too. I don't know what's going to happen. No. Okay, yeah.
I hope you can see there on the left. See, there's a small DVD there. I'm pointing with a pointer. That's the area it is rotating. There it just pops.
Yeah.
Now we will see that in slow motion. Look at the DVD, how it got completely bent actually.
2,500 frames a second.
It just pops like a balloon.
Fast enough to see what happened there.
This is in slow motion.
See it walking. Look at that. Whoa. Moving so much. Oh my god. Look at the shape of it. It's moving like the whole thing. Whoa! Oh god. Oh man. That looks amazing. It's just shattered tiny little bits. It's just like physics don't know what to do with the scene. It's just like, nope, no, I'm done. I'm out. I'm done. Oh, that's amazing. See that again. I've seen it.
And they're going to slow it down more, and
play back in 25.
They played that whole video for 4. They actually recorded for 4 seconds. It's such a high frame rate. If you actually see that in a normal speed, it'll take 10 to 12 hours. That whole size of the file will exceed like what, 20-30 GB or more.
Let's slow a minute.
I'll post the video in the group. You can check it out. So get some big face in there rotating.
Full speed ahead. Warp drive on.
There it's rotating.
Just that's fine. Turn. Is it? Yeah. Oh!
But it just pops.
You can actually see it warping. You jump.
You see it in slow motion there.
The actual moment where something happens, it takes forever to get to. Oh, that was awesome because you saw the actual shape of the CD and the cracks in it.
You can see how it starts at one point and spreads off.
The CD was spinning. So it was like a spiral effect on the CD. Like a turbine. That was cool. All right, so that was 60.
There. So you rotate something fast enough, it will get shattered. So that was this. All clear with this? No. Let's see. One more based on this, but it is actually a question on friction, but we use a similar technique there. We will do them together so that. Let's say we have a fixed cylinder. Fixed rough cylinder. Friction is mu. So we have a rope here. We have a block of mass M. And you're applying force F. Massless rope, but it is rough. And the cylinder is rough, huh? It's not smooth. So find F if the block is at rest. Let's get this. This is more of a friction question. But he always handled smooth pulleys. This is rough. Let's give it a try. How do we start this? The rope is massless. How does that affect the tension then if the rope is massless? Like how does the friction come? Let's see. Listen carefully. Actually, you get a range of answers. I told you this before. Whenever you hear the word friction and equilibrium, you always get a range. Now, imagine a situation where you're applying a maximum force, then the block will try to go up. So let me take that scenario. F max. Block tries to go up. So now if you look at this, I'll just separate the rope here so that you can clearly see the friction ka direction. So the rope is trying to go this way. So on the rope, the friction will be this way, dF. dF. So the friction will be in this direction. So this friction is actually, helping the weight mg. And here the weight was mg. So tension on the left end is mg, and the tension at the right end is F2. And beach mein you have a friction. So if I get the sum of all these frictions plus mg, that should be equal to F ka value. Is that making sense? Now, how do I find all these frictions? So see, now the technique which I taught you right now, we're going to use that. So this black thing which is there, the rope, we do the same story. Consider a small d theta. I'm just taking randomly anywhere. I'll take it from here. So at an angle theta, choose a small slice d theta. So we get a small slice here, r d theta. So just let me exaggerate that. I'll make it flat because it really doesn't matter. There is no gravity anyway. And if you look at the forces here, this will be tension. This will be tension T plus dt. So tensions will be different. So we have tension T plus dt. The story is again the same. This angle will be d theta by 2 and d theta by 2. And this time you also have a friction also additional. So on this small piece, you also have your friction df. This angle will be d theta by 2. This angle will be d theta by 2. And you also have a force, normal reaction dN. Please have a look at the free body diagram. This is clear? So two tensions, one normal reaction, one friction. Total 4 forces will be there on the small string RD theta. Now once we got here, I can resolve them into components. This will be T sine d theta by 2. This will be T cos d theta by 2. T plus dt cos d theta by 2. T plus dt sine d theta by 2. So in the vertical direction, we can clearly see dN will be T sine d theta by 2 plus tension plus dt sine d theta by 2. For small angles, I can write sine d theta by 2 is d theta by 2. Yeah, in this thing, these approximations are the key. And cos d theta by 2, d theta is so small, cos d theta will be approximately 1. It's like cos 0. So we get dn will be t d theta by 2 plus t d theta by 2 plus dt d theta by 2. Now d theta is only very small and you're multiplying another dt. This will tend to 0. Isn't it? Dx is very small. And if you multiply dx into something, you're multiplying another very small number. So we get dn is equal to tension into d theta. This is equation 1. In the horizontal direction, we can clearly see t plus sub in dt cos d theta by 2 minus d cos d theta by 2 is equal to df. Cos theta is anyway constant. I'll get dt is equal to df. But what is df? Mu into dn. Let me show it in the next page. You guys should definitely go through the today's note. It's like pretty heavy, like there's a lot of stuff. And this would be dt is equal to mu, and dn we proved it is dd theta. So this will be dt by t is equal to mu d theta. Now when you integrate this on both the sides, dt by t is equal to mu integral d theta. When you go from 0 to pi, this value will go to this will go from F to mg. The tension will vary like this. I think I forgot a minus sign here. I wrote reverse, I guess. This is minus plus and this is this. So dt will be minus df because I took these two on the same side. No? This will be ln tension. Limits will go from F to mg. That will be minus mu into theta. Limits will go from 0 to pi. This will be ln mg minus ln f is equal to minus mu pi. This will be ln f pi mg is equal to mu into pi. We get f is equal to mg into exponential e power mu pi. This is your maximum force. It actually depends on exponential. If I take the friction in the reverse direction, for F minimum, dF is opposite. So you'll get F minimum will be mg into e power minus mu pi. So the answer will lie between mg e power minus mu pi by mg e power plus mu pi. So basically this was the main catch there. So what is happening, for every segment, the tension is increasing. The increasing tension is increasing the normal reaction. The increased normal reaction is increasing friction. That friction is again increasing tension. That tension is increasing normal and is again increasing friction. You're getting what is happening? The function is increasing itself continuously. And the function is rapidly increasing. That's what we call as exponential. So if I had to give you a general formula for this, let's say if you have a rope like this, where theta is the angle made by the rope in contact. And let's say if you're applying something like, let's say, some F naught, and if you are applying here, let's say some F. So if you're trying to pull this and you're trying to balance F naught there. So this F pulling force will lie between, so depending on if you want to pull this, F pulling must be equal to F naught into e power mu theta. So you need to apply this much force in order to move the rope. This is the minimum force required to move the. This is a pretty big value. Matlab, if you see that, required to move. So that is exponential. Let's say mu ka value is half. And let's say if you take a cylinder and if you tie it 3 times, then the angle will become 3 times 2 pi. That would be e power 3 pi. Pi is almost 3.14. That is e power 10. That is 2.7 ka whole power 10. That number goes to something like 3000. That means if you apply 1 Newton here and if you make the rope go 3 times, in order to pull the rope, you need to apply 3000 times more force. So next time, if you're ever playing this game, right, tug of war, you can't win the game, but you can also make sure not to lose the game. All you need to do is take a rope, make it go once, twice, thrice, 4, 5 times, and then you catch it here. Even if you apply 10 newtons here, these people have to apply a force of 20,000, 30,000 newtons to pull the rope out. Even before the rope comes out, the pole will break first. So you can generate a very high tension using this technique. If you have ever seen, I don't know if you have ever seen in ships and all, right, movies we must have seen, how they tie the knot to the rope. Let me see where it is. This is how they tie the rope, if you have ever seen. Can you see how they're tying the rope there? So by tying the rope multiple times round, it's very difficult to pull the rope out. You get a very high tension. So this is a technique we use when you're tying something. You make it go few rounds. This is a pretty good question. This is based on the same technique that I used here. So should check it out. So that's a bit about it. So again, today's class, especially what we did here, right? Go through this integration, this differentiation, but frankly speaking, you don't need it because this thing is not in the portion. And whenever they ask this question, they did ask few times. I'll show you how the question will look also. The reason to show you, right, is if when it comes in the exam, you will not get shocked suddenly. That was the reason. Let me show you how they ask these questions. This I think 2016 or something. Look at the question here. It's not clear, but look at this term here. Can you see? This is the thing which I derived. F rotation, that is a rotational force, is the inertial force plus 2mv omega plus m omega square r. So normally when they give this question in the exam, because Coriolis force is not in the syllabus, they will give you this equation. They'll mention the force is this. Now solve the problem. So even without knowing what I taught you today, you can still solve this question. But generally when people see this, they psyched out and they're like, oh, what is this? Something new. And also it is better to have an idea what we are talking about. So when this question comes, I will teach you again. So don't worry about it. But Firbi, please go through this, what we did today. So the main thing is, like I said already, the main thing is this new relative velocity. You can also create relative velocity by rotating your head even without moving. So just go through that part. And then there are 4 different pseudo forces. Centrifugal force is a part of it. This pseudo force we studied in laws of motion. This is your circular motion centrifugal force, which you studied in school. The remaining 2 are those 2 pseudo forces. And go through this example. I think this should make things very clear. And then when we solve problems, we always stand on the center. And yeah, this is a good one, 16th one, and 17 and 18. So just revise it a bit. The next class, when we catch up, we will do more on this thing. I think we should take another 2.5 classes. We should wrap up the chapter, maximum 3 classes more. But I think the major thing is gone. We will do more on this. 3 classes we will take more to finish it off. Okay, with that, we'll wrap up for the day. Do remember there's a test online on Friday, so make sure to give it. So any doubts in today's class notes, anything else, please stay back and ask, or else you're free to leave. I'll see you guys again next Monday. So take care, stay safe.